Uh, Hello, everyone, and welcome to the first live interaction session of the NPTEL course Network Security. Uh, so in the link that was provided to you for uploading your questions, there were no questions uploaded on through that link. Uh, if you have any queries right now, please type them into the chat window. Any questions? Please type them in the window. So while we wait for questions, we'll start with our discussion of some examples. Both these examples are in the context of RSA. So we start with the first example. There are two parties, Alice and Bob, who communicate with each other, and there's an intruder, Trudy. And we know that Trudy's RSA keys are as follows. NT is 33, DT is 3, and ET is 7. Uh, yeah, so 2D's RSA keys are as follows. NT is 33. So I recall that NT is a modulus, then DT is 3 and ET is 7. So the public key of 2D is NT comma ET, which is 33 comma 7, and the private key is NT comma DT, that is 33 comma 3. Now, 2D, suppose 2D finds out that Bob's public key is NB equals 33 and EB equals 3. So uh, Bob's public key is well known, and it's also known to the intruder 2D. And in this case, it happens to be 33 comma 3, which is exactly 2D's private key. So in this case, can the question is, can 2D use this information to read encrypted messages that are directed to Bob? So how can 2D use this information? Recall that we discussed earlier that uh, encryption and decryption in RSA, they can be applied in either order, and still the algorithm works correctly. So typically we apply first the encryption algorithm and then we decrypt. That is, we first apply the public key and then we apply the private key to decrypt the message. But if we use a reverse order, that is, first we apply the private key and then we apply the public key to the result, then still we get back the original plain text. So we use this fact here, and 2D can decrypt messages directed to Bob using this fact, because consider a message that is encrypted with Bob's public key, that is 33 comma 3. We have noted that this public key is the same as 2D's private key, 33 comma 3. So encrypting using Bob's public key is equivalent to applying 2D's private key to the same. That is, KT minus of M is the ciphertext, and now 2D can just apply her public key to the result. That is, 2D can apply this NT equals 33 and ET equals 7, and that will result in the original plaintext message. So in this case, 2D can use the fact that NB equals that Bob's public key happens to coincide with 2D's private key, and this decryption technique here exploits the fact that the operations of encryption and decryption, that is application of public key and private key, can be applied in either order, and still we get the algorithm still works correctly. Okay, so that concludes our first example. So there don't seem to be any questions. Okay, so let's move on to the next example. So in this example, again we have a public key system which uses RSA, and suppose you intercept the ciphertext C equals 10 that is sent to a user, and the public key of the user is E equals 5 and N equals 35. So we want to know what is the plaintext M corresponding to this ciphertext of 10. So using just the ciphertext and the public key, it is typically not, it is, as we know, it's computationally infeasible to calculate a plaintext. But in this case, N is 35. It's just an example. So we'll just demonstrate how the plaintext can be obtained from the ciphertext and the public key, since the exponent is very small. So since N equals 35, we note that the prime factors of N are P equals 5 and Q equals 7. So we get that by just factoring the prime, by factoring the number. So Z, which we discussed during the lecture videos, Z is defined to be P minus 1 times Q minus 1. And that is, in this case, 4 into 6, that is 24. So for decryption, we require some number D such that E times D mod Z is equal to 1. So such a number for these values of E and Z, these values of E and Z, namely 5 and 24, such a value of D is 29. So it can be checked that 29 times 5 mod 24 is equal to 1. So the plaintext is this M equals C to the power D mod N. So just substituting, we can substitute C equals 10 and D equals 29. So 10 to the power 29 mod N, but N is 35. So hence we get this expression for the plaintext, and we can simplify. Yeah, and we can calculate this. It's easy to calculate this this quantity 10 to the power 29 mod 35, and that's the plaintext. So in this case, since the modulus was very small, we could just use brute force to calculate the plaintext corresponding to the ciphertext. Okay, so this concludes our discussion of the examples about RSA. So any questions, please feel free to ask them. So any questions about the examples or any of the lecture videos that have been shared? Okay, so you also know that you can also ask your questions through the interface that has been provided to you. So we have been receiving various queries, and we have been responding to them through that other interface. So you can ask your queries through that interface as well. Fine. So if there are no other questions, then we'll conclude this first live interaction session. Thank you. Right. Thank you.